Continue on Physical Chemistry, Chapter 19. This is Section 8 now. So now we'll talk about many electron atoms on the periodic table. So remember, lithium is the element with 3 protons, and therefore, as a neutral atom, it'll also have 3 electrons. So look at this graph. We have the nucleus here, and then we're going to have electron 1, electron 2, and electron 3. So the Hamiltonian will have to have 6 terms just for potential energy. Potential energy from electron 1 to the nucleus, electron 2 to the nucleus, electron 3 to the nucleus, and then of course electron 1 to electron 2, electron 2 to electron 3, and electron 1 to electron 3. And then of course I denoted how to show what these potentials are. So you also notice 3 of these are attractions between the nucleus and the electrons, and then 3 of these are repulsions between fellow electrons because they all have the same charge. So we have plus e prime squared over r12 plus e prime squared over r13 plus e prime squared over r23 minus z e prime squared over r1 minus z e prime squared over r2 minus z e prime squared over r3. And then we have minus h bar squared over 2m times del 1 squared plus del 2 squared plus del 3 squared. That's the kinetic energy of the 3 electrons. So using determinants doesn't work. So see handout 96-3. So 2p2 splits up into 3p, 1d, and 1s due to electron interactions. So we have for L equals 1, s equals 1/2 plus 1/2 equals 1. So 2s plus 1 is equal to 2 times 1 plus 1 is equal to 3. That's a triplet state. And then p2, that's going to be s equals 1/2 minus 1/2 equals 0. And of course this is pronounced triplet p. So s equals 1, L equals 1, J is equal to L plus S, so 1 plus 1 is equal to 2. That's J max. Now J min is going to be the absolute value L minus S, which is 1 minus 1, which is equal to 0. So total degeneracy or multiplicity, we get 2L plus 1 times 2S plus 1. So for triplet P, we get L equals 1 and S equals 1. We have 2, 1 plus 1 and 2, 1 plus 1. We get 3, 3 equals 9. That's the total degeneracy. So let's talk about a lithium atom. So we have the Hamiltonian is equal to 3 terms for kinetic energy, plus 3 terms for attractive potential energy, plus 3 terms for the repulsive potential energy. So that's the exact Hamiltonian for lithium. Of course, the repulsions are what make it hard to solve. So the approximate Hamiltonian is going to be just the Hamiltonian for electron 1 plus the Hamiltonian for electron 2 plus the Hamiltonian for electron 3. And of course, APP means approximate. So there are wave functions for that. So we get psi approximate is roughly equal to psi 1 times psi 2 times psi 3. So each is a hydrogen-like wave function. And remember, hydrogen-like means just 1 electron. So we basically assume the 3 electrons are independent. They don't repel each other. So we have psi at the ground state is equal to 1s1, 1s2, 1s3. It's 1s because it's hydrogen-like. And that's symmetric. So Pauli says, including spin, it must be anti-symmetric. Now the procedure for helium doesn't work for lithium. Instead, we need to use determinants. So let F, G, and H be 3 spin orbital functions. So we have psi anti-symmetric is 1 over the square root of 6 times this determinant. F1, F2, F3, G1, G2, G3, H1, H2, H3. Now 6 is n factorial. Oops, so n is equal to 3. That's where the 6 comes from. So this is called a Slater determinant, named after John Slater. So the middle column is negative when we take the determinant. So for the lithium atom, we have psi is 1 over the square root of 6. This determinant, 1s1 alpha 1, 1s2 alpha 2, 1s3 alpha 3, 1s1 beta 1, 1s2 beta 2, 1s3 beta 3, 1s1 alpha 1, 1s2 alpha 2, 1s3 alpha 3. That's equal to 0. It equals 0 since column 1 is equal to column 3. Now the Pauli exclusion principle says no more than 1 electron can occupy a given spin orbital. Now for an orbital, we have N, L, and M are those terms, right? So for spin orbital, we have, or quantum numbers is what they call. For spin orbital, we have N, M, L, N, L, M, and MS. Remember, MS is plus or minus 1/2. So we need to change the third column, so we remove one S and replace it with 2S. So the third electron will be in the next orbital. So we could have used beta instead of alpha in the third column. So the ground state is doubly degenerate. So we have lithium 3, that's 1s2, 2s1. So this first, the 1s2 there, that's the filled subshell, so we're going to ignore that. So we're going to derive the term symbol. So the 2s1 means there's one electron in the 2s orbital. So we have L equals 0, so that gives us our S code. So S 1/2, S 1/2, so we get 2S plus 1 equals 2 1/2 plus 1. That's equal to 2. That's the multiplicity. So 2 for multiplicity means doublet. So now we have 2S, that's the code for the ground state of lithium. So we have degeneracy of that state is 2L plus 1 times 2S plus 1. That's 2 times 0 plus 1, 2 times 1/2 plus 1. So we get 1 times 2, and that is equal to 2.